Hello Mindsetters, welcome to today's Grade 10 Physical Sciences show. I'm Katleho. Today we have a special revision session for you guys, which is on the periodic table as well as chemical bonding. We have selected highlights from lessons shown earlier in the term just to help you guys revise all the work we've done together in the first term. You can download all your notes and schedules for today's lesson on learnextra.co.za/live. Guys, you can also post all your comments, all your queries, all your questions, most importantly, on our Facebook page, which is facebook.com/learnextra, as well as on Twitter, which is @learnextra. Guys, please, without further ado, let's get on with today's lesson.
Let's get stuck into electron arrangement. Electrons are found in energy levels. And when we say energy levels, we're thinking those ones that are closest to the nucleus will have the least amount of energy. And as the electrons are found in energy levels further away from that central nucleus, they will have to have higher energy. They would be moving in regions of space that are called orbitals. Now let's just take this little bit away, so that you can note this very important word, orbitals. Orbitals are regions of space where an electron could be found. There's a higher probability of an electron being found there. They are not spherical rings or different shapes, but they are clouds, electron clouds where electrons could be found. There are various ways that we can represent electron configurations, and we're going to discuss 3 of those today. We're going to look at a concentric circle model, a Lewis diagram, and an Aufbau diagram, and this is also called an energy level diagram. You could very easily in an exam question be asked to draw these models, and so not only are they important for your understanding of bonding and everything else that's going to come in chemistry, they are important in just in terms of answering exam questions. You will be asked to draw these. So let's start with the simplest, the concentric circle model. For the concentric circle model, we are considering energy levels with the electrons found on those energy levels or in those energy levels as circles, concentric circles. And in the first ring, 2 electrons can be found. In the second ring, 8 electrons can be found. And in the next ring, third ring, 8 electrons can be found. And we're not going to go much further than that. So let's have a look at how this would be done. I've got an example here of neon. Neon has 10 and a number 20. What do those numbers mean? We spoke about this last week. The 10 represents the atomic number, okay, which means the number of protons, positive, okay. The 20 represents the atomic mass, and I'm going to change color to indicate that it would be atomic mass. And for atomic mass, you are thinking that is the protons and the neutrons. As we have a look at that, if it's got 10 protons, for this atom to be neutral, if it's got 10 protons, how many electrons must it have? Well, for it to be perfectly neutral, it should have 10 electrons as well, so that overall the charge is 0. There is no charge. So let's go with this atomic model and fill in the electrons. We're going to fill them in as little circles. I said 2 in the first, so 1, 2 in the first. Now we go 8 in the next, so 1, 2, 3, 4, 5, 6, 7, 8. Check with me quickly. Is that a total of 10? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A total of 10 electrons shown in those energy levels. Now, the reason I've shown this one to you specifically is because I want to indicate to you how to arrange them. The electrons I want to recommend is that you put those electrons on the compass points as you work your way around. It's going to be very helpful to you because it's going to show how many spaces there are available for bonding. And we often use something called the Octet Rule, which is saying if you've got filled outer energy level full of, in this case it would be 8, and apart from helium, which has only got 2, so it's only the 2 in the central ring would be filled. If it's got this filled outer energy level of 8, almost like 8 people sitting around a table, there is no more space for any electrons. So there's no need for that atom to bond. And neon actually is one of those noble gases. It doesn't bond with anything else because it's got a stable electron structure, a filled outer energy level. So we've got 2 key words that I want you to note: valence electrons and core electrons. What do you think the core electrons would be meaning? The core electrons must mean the inside ones, right? So the core electrons in this case would be neon's 2 core electrons. They would be ones that are found in the inner energy levels. Whereas the valence electrons, that was the core, the valence electrons are those that are found in the outermost energy level. We're going to use those 2 words a lot as we discuss electron structure. Let's move on to the next, a few of these in terms of practice. Now, I've included here Lewis diagrams. Now, Lewis diagrams are even simpler than the concentric circle model because they only consider the outer ring, the valence shell, which is helpful. So only valence electrons are shown as either dots or crosses around the symbol for the element. Let's consider carbon. Now, you're going to need to know how many protons carbon has so that you can work out how many electrons carbon has. So I've got a periodic table. Let's reference it quickly. Find carbon. Carbon is over here, number 6. That 6 is the atomic number or the number of protons. So we can go back and write carbon and note it has 6. So let's try just practice the original one, where we did the concentric circle model. So I've got 2 rings that I'm drawing, and we're going to go 1, 2 in the first, and now I'm suggesting you work with compass points as you go around. 1, 2, 3, 4, 5, 6. So it's got 2 core electrons and 4 valence electrons. Now, for this Lewis diagram, we only need to draw the outer ring, the valence electrons, because those are the ones that are going to be involved in bonding, involved in interacting with other elements. So, for a Lewis diagram, we're going to just draw, and I'm going to use little crosses to indicate those 4 valence electrons. Let's go on and try another one. We're going to work with oxygen. So I'll change pen color and let's work with yellow for oxygen. Oh, that was, I think, a little bit too far. Let's find oxygen again. Oxygen, let's draw its valence electron, the ring structure, and I need to go to a periodic table, find oxygen. We've got oxygen over here, oxygen number 8. So atomic number, and I'm going to write up here 8 protons, 8 electrons, because overall it's an oxygen atom, so it must be neutral, no overall charge. Let's go. If we've got to make 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. Now, as I suggested to you, you want to work around on the compass points because it's going to help you to identify where there are spaces for the substance to bond. How many electrons would it gain or lose in order to make sure that it gets to a filled outer energy level? So let's have a look for oxygen here. And we've got oxygen. It's got a lone pair and another lone pair. These guys is what I'm going to call a lone pair. They have paired up already. But notice there is space, two separate spaces where oxygen can take up extra electrons. And so usually when oxygen bonds, it's going to form an O2 minus ion. We'll come to that in a few weeks as we look at bonding. Let's keep going. The last type of model I need to look at is sometimes called an Aufbau diagram or an energy level diagram. Now these tend to be the most complicated, so let's spend some time working on those. Aufbau diagrams have these little box structures where we have not just energy levels, but the shells in which, or the orbitals in which those electrons would fit into. So you have a 1s, a 2s, 2p, 3s, 3p, 4s, and it can continue. This first band is the first energy level. The next band is the second energy level. The third band, the third energy level. But in terms of filling up, we're going to always start from the bottom and fill up with electrons. Now, the electrons are shown as little arrows going up and going down. The reason going up and going down is because those electrons, in order to not have a significant repulsion, they are always aligned with opposite spin. So the one spins one way, the other spins the other way. Okay? Now, there are a couple of rules that we need to follow as we work through Aufbau diagrams. Each orbital or little block can only hold 2 electrons, called an electron pair. An electron will always try to enter one with the lowest possible energy level. So you're going to start from the bottom and work your way up. An electron will occupy an orbital on its own, because remember, these are electrons, and so they're going to, if they have the same charge, repel each other. So they will start with their own space, and then, if necessary, they will pair up. So an electron would rather occupy a lower energy level with another electron before occupying a higher one. If it has to, it will pair up. In other words, with one energy level, electrons will fill an s orbital before starting to fill higher up p orbitals. And the s subshell can hold 2 electrons, while the p subshell can hold a maximum of 6.
Okay guys, I hope you're really enjoying this revision session. If you are struggling and need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. Now it's time for a break, so don't go away. We'll be right back. Welcome back, guys. I hope you are getting into the idea of revision. Please let us know how you are doing. I'd love to chat to you guys either on the page or on Twitter. Enough of the chat. Let's get back to our revision now.
We're going to start with some questions on Aufbau diagrams. Remember, they could be asked as energy level diagrams, because as you have a look at it, and I've started with the blocks there, these bands are showing the various different energy levels that a substance would have. So we've got a start with nitrogen. They're asking us to draw an Aufbau diagram or an energy level diagram for nitrogen. Now, across to your periodic table, find nitrogen. I'm going to need to just clear these so that we can see, because nitrogen is down there. Nitrogen in the middle, 7. Let's go back and start working with nitrogen. It is 7 and 14. And let's just write that again. Nitrogen 7, 14. 7 meaning standing for 7 protons, and for this thing to be overall neutral, it must have 7 electrons as well. Now, if we've been asked to draw these 7 electrons, let's go to an Aufbau diagram and write them in. Across here, I've already got the blocks drawn. Sometimes that takes a bit of time, so I've already got them drawn. That would be 1s, 2s, 2p. Now, I could draw a little dotted line here to indicate to you that this is the first energy level, that is the second energy level. The second energy level has 2s and 2p. Now, I didn't speak to you earlier about what those mean. The s is standing for a spherically shaped orbital. So almost like a ball, those electrons have a sphere in which the orbitals is shaped in. The p is a very interesting shape. It's like a figure of 8 or a almost like a dumbbell shaped figure, whereas, and it goes up and down. You'll notice there are 3 of them: up, down, left, right, and forward and backwards. So these 3 or p orbitals together can carry 6 electrons. Let's fill in the nitrogen, and I've got these boxes. Remember, I've said to you we start from the bottom and we fill in. So 1, opposite spin, 2. That whole s orbital, that whole first energy level is now full, so we have to go to the second energy level. The next one, 1, 2, so 1, 2, 3, 4, 5, 6, 7. That is the 7 valence electrons, the 7 electrons for nitrogen. Now let's have a quick look at it and identify that as I drew these in, I didn't put the 2 of those in one of the p orbitals. I separated them out, putting 1 in each of those p orbitals, because they want to be as far away from each other as possible within that same energy band. So coming back here, how many valence electrons does nitrogen have? Well, valence, remember, by valence I'm speaking about those outer electrons, and it would be everything in this top energy level. So 1, 2, 3, 4, 5. 5 valence electrons. And nitrogen can make 3 bonds, because if you look at it, it's got 3 open spaces waiting to bond. Let's turn down to another one. We've got it there. And let's look at a different one. This is for oxygen. And oxygen, I'm going to come back. We've used oxygen a few moments ago. It was oxygen 6. So let's write it up. Oxygen O had 6 and, oh, I don't think it was 6. Just check me quickly. I think it was 8. Oxygen. I was looking at carbon for a second there. We are considering oxygen, which is 8. So going back here, this should be oxygen 8 and 16. Specifically going back to the question, and I've thrown this question into you almost as a bit of a curveball, because I want you to think about it. They have asked us not for an oxygen atom, but for an oxygen ion. Now, an oxygen ion's formula would be O2 minus. The reason it's going to be 2 minus is because it's gained or taken up an extra 2 electrons, and that's vitally important. So, as we draw it, we're going to have 8 protons, but if there must be an overall 2 minus charge, how many electrons must there be? Well, overall 2 negative, so it must have 2 more, so therefore 10 electrons. Are you all happy with that? Let's come across and fill in our Aufbau diagram. So 1s, 2s, 2p, and we're going to fit these in. So in the first, 1, 2. In the second, 1, 2, 3, 4. Count so long. 1, 2, 3, 4, 5, 6, 7. Now we can start pairing up. 8. Are you happy that that would have satisfied the 8 electrons that oxygen originally had? Now, if it's taking up an extra 2, where are those extra 2 going to fit? They would be here, 9, 10. So overall, this oxygen atom has gained an extra 2 electrons, and so is overall 2 minus. You must be able to do these for ions as well as for atoms. And if I would recommend to you, as you work through these, and I've made a quick note here, if you're asked to draw alpha diagrams or energy level diagrams for ions, I would recommend draw the original atom, as I did. Then consider, if it's positive, it must have lost electrons, because it has less electrons than protons. The proton number is outweighing, so it must have given away or lost electrons. Whereas, if that ion is negative, then it must have gained or taken up extra electrons. Remember, electrons, although we're adding something, we're adding extra negatives. So it's taking up extra negatives, and so you would be able to fit those in on your Aufbau diagram. Usually when things are bonding, they are trying to make sure that that energy level is full. Okay? So if they're giving away, it's normally giving away 1 or 2 from the outer ring, so that what is left behind has a filled outer energy level.
Now it's time for a break, so don't go away and we'll be right back. Welcome back, Mindsetters. Today we are doing revision. Even though we are selecting highlights from previous shows, you can still follow me on Twitter @LearnExtra, or post or comment on our Facebook page, facebook.com/LearnExtra. Right now, let's do some more revision.
Let's turn and see how covalent bonding would work. Now, covalent bonding, and the idea of co would be together. Okay, so covalent bonding would be those valence electrons are together, covalent. So covalent bonding would happen when you've got sharing of the outer valence electrons. If an electron is shared, it means that it will spend time moving in the orbitals between the two atoms. It will spend its time moving in the electron orbitals around both those atoms. And it would occur between non-metal and another non-metal atom. So if you can think about these two atoms having a little tug of war. We've got a shared pair of electrons and they're pulling between both. Sometimes they would be perfectly matched. Okay, so if you think something like a diatomic element, like chlorine, which is the example I've got, where you've got two atoms of exactly the same type. If they're the same type, well then one is not pulling any stronger than the other one because they're exactly the same, so they would share equally. Whereas we also have something called electronegativity, which you'll deal with later in grade 11, where there is an unequal sharing of electrons. And we'll look at that a little bit later. But the idea behind it is simply that those atoms are close enough together that their orbitals overlap and there is sharing of electrons. So let's draw in, and I've used chlorine. Notice chlorine on the periodic table. We'll go and find it quickly. Chlorine is over here, right at the end. It's in group 17. So how many valence electrons must it have? Well, 17 minus the 10 from the transition elements is going to give me a total number of 7 valence electrons. So let's go and draw those in. Now I'm using a concentric circle model, but I'm simplifying it almost like a Lewis diagram, and I will draw in those 7 valence electrons. So let's draw them in as little dots. 1, 2, 3, 4, 5, 6, 7. Now, to make this slightly easier to visualize, I'm going to take these out and actually just draw them. So 1, 2, 3, I've got that for, 1, 2, 3, 4, 5. 6, 7. And the next one, 1, 2, 3, 4, 5, 6, 7 valence electrons. What I hope you can see is that in this picture, I've got these two guys here that are unpaired. They don't have a partner. Okay, so those two valence electrons are not paired. And if I just take that little circle out, what I hope you can see is that if we've got these little pairs, and I'm going to draw them quickly. There we are, 1, 2, 3, 4, 5, 6, 7. I'm going to draw this next one in a different color. 1, 2, 3, 4, 5, 6, 7 for those 7 valence electrons for chlorine. What I'm hoping that you see is here, in between, there's a green one and a little purple one that are making an electron pair. And so this chlorine atom that I've drawn in blue has got 8 electrons in its outer energy level. The one in purple has also got 8 electrons in its outer energy level. So between them, they're more stable. But that set is a shared pair of electrons. Another way we could draw this is to indicate those electrons as just an unpaired electron where they are almost free to move, and we could slide that over and indicate them as a shared pair. And now we're going to move on to consider some ionic bonding and metallic bonding. So come with me to the page. Ionic bonding. Ionic bonding is when there is an exchange of electrons. Okay? So what do you understand by an exchange? Well, if I went and exchanged my jacket for something with a friend, I would swap it. Okay? So give one thing and get something else maybe. When you speak about exchange of electrons, we've got something giving away electrons and something else taking up electrons. So if an electron is exchanged, it means it is transferred from one atom to another. Okay? In other words, one atom, let's jump down here, loses an electron, that's critical, while the other one gains an electron. Now, that would mean that something is left with one electron short and something is left with one electron more. Well, what's that going to form? What's going to happen with that? Well, something is going to be left overall positive and something else would be overall negative. And what happens with positives and negative? Well, you know, opposites attract. So there's going to be that attraction between those ions, pulling them together. Positive and negative ions are formed, and ions are anything with a charge, so a charged particle. Let's have a look. This would happen between a metal and a non-metal. Go back quickly to covalent. Read your notes. What did we say with covalent? Covalent was specifically a non-metal with another non-metal. So this is now a metal and a non-metal. Which would be willing to give electrons and which would be willing to take electrons? That's what I want you to think about a little bit. Let's go to an example and we'll see what we mean. The example I've given here is table salt, NaCl, sodium chloride. And I've asked you to fill in valence electrons and the respective charges. So going to your periodic table, we're going to see we've got sodium and chlorine. I've already circled it there. And as you come back, I want you to notice that sodium has 11 protons and 11 electrons. So overall, 11 protons, 11 electrons, and it's going to give me an overall charge of 0. Does that make sense? Because you've got 11 protons, 11 electrons, totally balanced, no charge. It's neutral. I want us to fill in valence electrons. Now, jumping back to the periodic table, if we are considering valence electrons for group 1, how many valence electrons does it have? Well, simply 1. So we can draw that in. Let's jump across here and pick purple. I'm going to draw in 1 valence electron there. Then we come across to chlorine. We've just discussed chlorine, and we worked out that it was in group 17. 17 minus 10 gave me 7 valence electrons. So let's pick another color, and we'll go 1, 2, 3, 4, 5, 6, 7 valence electrons. Notice this has got one space or opening that is available for bonding. Okay, it's got one space, only needs one more electron to fill that outer energy level for chlorine, whereas sodium's got one to give. So what do you think is going to happen? Well, overall that was neutral. Let's go across to this one. The outer electron for sodium will be given away, and chlorine has got its 1, 2, 3, 4, 5, 6, 7. But now it's got an extra one, and so it is left overall with a negative charge. Now, I think let's just shorten these brackets. Why do I say an overall negative charge? Well, because it's got an extra electron, and electrons are negative. So if you come across here, I've written 35 protons, because that's how many protons it has, its atomic number. And then it's now got not just 35 electrons, but an extra one. So 36 electrons, and so it's going to be a 1 minus charge. Whereas coming across to sodium, sodium has given away that electron, so overall its charge will be positive. And let's look here, protons, 11 protons, only 10 electrons now, and so it's going to form a 1 plus charge. So these two things are oppositely charged. One is positive, one is negative, and they're going to be attracted towards one another. So those ions, charged particles, because they're oppositely charged, will be held together by strong electrostatic forces of attraction. Very important, because they're oppositely charged, they pull together and attract. And those ions are arranged in what we call a crystal lattice. Now, a crystal lattice is a regular arrangement of particles in a repeating pattern. So as you have a look here, it's a bit of a 3D diagram. We've got the sodium pluses, the chlorine minuses, and if you think if you've got one sodium, it's going to have chlorines above and below and to the left and to the right and forward and backward in an alternating pattern, as you can see there. Because of that positive and negative charge, there are very strong what we call ionic bonds. Ionic because these substances are now ions. They are oppositely charged and they hold together. Let's turn over and look at metallic bonding. Now, metallic bonding is quite different to covalent. Covalent was sharing, ionic was a transfer of electrons. Metallic is quite different from both of those. In a metallic bond, we have valence electrons that are what we call delocalized. Now, I want you to think about the word local, what the word local means. If you buy local, if you in your area, within that space is everything local. Now, if something is delocalized, it means it's free to move. It's not in a specific orbital, but it's now free to move around, meaning that the atom's electrons do not stay around that one nucleus. In a metallic bond, the positive atomic nuclei, which would be often called the atomic kernels, are surrounded by a sea or a cloud of delocalized electrons, which are attracted to all the nuclei around them. Have a look at the picture. You've got those positive kernels. I'll just highlight one. That's a positive kernel. And notice you've got these electrons that are interspersed around them. They are free to move around them. Think about a little bit about what this will mean. It means that metallic substances are good conductors of electricity. Why would that be? Well, they've got all these electrons that are free to move, that can conduct electricity, that can carry it around. Similarly, they are very good thermal conductors, which means they can they allow the flow of heat or the movement of heat. So notice you've got these free electrons. They are able to move around those positive kernels. Let's have a look at some questions next, because I'm sure you're dying to answer some questions. As we go, let's go. Question 1. Represent the formation of carbon dioxide. Now, carbon dioxide is made of what? Carbon atoms and oxygen atoms. The molecule CO2 using Lewis diagrams. Now, as we have a quick look here, I want you to note carbon, and I'll just draw carbon and oxygen. Okay, I'm going to draw them in that arrangement because that's how I know that they're arranged. But I want you to think about this a little bit. Carbon, is it a metal or a non-metal? Oxygen, is it a metal or a non-metal? What type of bonding is going to occur? And the answer is that carbon is a non-metal. Oxygen is a non-metal. So the type of bonding that will occur will be covalent bonding. There will be sharing of electrons between these. And I've given you a bit of a hint, but let's start by drawing the Lewis diagrams of the individual atoms. Okay? And I'm going to jump across back to our periodic table. Let's clear some of these so we've got some space to work. And I want us to identify oxygen, 8, an atomic number of 8, carbon, an atomic number of 6. Carbon is in group 14. Sorry, oxygen is in group 16. So 14 would mean 4 valence electrons. Oxygen is in group 16, so 16 minus a 10 will give me 6 valence electrons. Let's go and fill those in immediately on my page. So we'll do carbon first. 1, 2, 3, 4. 4 valence electrons. I'm going to pick a different color. Let's choose blue, and we're going to do, oxygen. Oxygen, and I'm going to draw little crosses. No, those are, I think, a little bit big for crosses for oxygen. Oxygen, 1, 2, 3, 4, 5, 6. And let's do the same on this side. We've got 1, 2, 3, 4, 5, 6. Now, how is this thing going to bond? Well, let's have a look at it. The carbon has got 4 unpaired electrons. The oxygen has got 2 unpaired electrons, which means it needs to make 2 bonds. And what's going to happen with these is that those 2 will bond, and those 2 would bond. And similarly on this side, well, I would need to rotate that. We would have a bond. Now I'm just going to draw a line across and across. So I need to redraw my diagram because that's looking quite messy. And we can do carbon in the center with its 2 electrons and its 2 electrons on the other side. Notice those are not paired, those are unpaired. But to make sure my diagram works nicely, 1, 2, 3, 4, 5, 6. I'm going to need to take these out. We had 1, 2, 3, 4, 1 there, 5, 6, and again here 1, 2, 3, 4, 5, 6. Electrons, just so you don't get confused by that little dot, we have a pair there and a pair there, and then another pair and another pair. Now, because we've got double pairs between those 2 atoms, we're calling them a double covalent bond, because that's a covalent bond and then there's another one. So it's a double covalent bond. But there actually happen to be 2 sets of double covalent bonds. And I've made a note on that for you. This is an example of double covalent bonds being formed where 2 pairs of electrons are shared between atoms. In this case, there's 2 sets, one with the 1 oxygen, or double with the 1 oxygen and double with the other oxygen. Let's turn and tackle another question, because questions is certainly where we learn a huge amount. Let's go with this one. we've got given the following Lewis structure where X and Y each represent a different element. We don't know what the element is, but it's a different element. What is the valency? Now, valency is bond number of how many bonds the substance can make. The valency of X, and have a look, X is making one bond, X is making one bond, X is making one bond. So the valency of X would be simply 1. What is the valency of Y? Well, come across. Y is represented with its electrons with these little crosses. Now, the one at the top here, that is what we would call a lone pair. Okay, they're already paired up, they don't need to pair at all, but it's making a bond 1, 2, 3. So its valency is a valency of 3. So 3 there. And the last question, which elements could X and Y represent? Well, this is an interesting one. Let's go jump across to our periodic table, and we've got X can make a bond of with 1, and Y can make 3 bonds. So I'm going to have a look and see where would that take me. Well, sorry, let's just clear those. I'm going to suggest to you, and let's just write in here 1, 2, that's going to be 3, 4, 5, etc., 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 10, 11, 12, that's number 13, 14, 15, 16, 17, 18. Okay, so as you have a look there, what has a valency of 3? What could make 3 bonds? And it's probably something here in group 13. Remember I said 13 minus the 10 can make 3 bonds. So it's probably something in group 3, it could be. Or, better yet, it could be in group 15, because that would be able to make 3 bonds. And I think the substance is probably nitrogen bonding with hydrogen. Would that work? Yes, it would, because go back and have a look at what the substance was. It had a valency of 3, but it's got those 2 extra, that extra lone pair. So it's got a valence, it's got 5 valence electrons, which would make it in group 15, not in group 13. Do you recognize how your reasoning has to work? Go back and look. This has a valency of 3, but it's got 5 valence electrons, which would make it in group 15, not in group 13. Okay? So Y is probably going to be, let's jump across, nitrogen, which has got 1, 2, let's draw them as little crosses, 3, 4, 5, with hydrogen, which can make 1, 2, 3. And this thing, NH3, is called ammonia. So it's quite a common substance, as you were to look at that. And I would suggest that it's going to be nitrogen with hydrogen to make up those 2. So let's go back. Which elements could X and Y represent? Well, it could be anything. X could be anything in group 1, and the Y could be anything in group 15.
Guys, we've come to the end of today's show. Thank you for joining us and chatting to me on our Facebook page. Remember, you can visit our website at any time that you want to get the notes as well as watch the videos. The website is www.learnextra.co.za/live. And if you're stuck, remember you can send an email to helpdesk@learnextra.co.za and tell us where exactly you're stuck so that we can help you. Don't forget to look out for more news on Library Month on our Facebook page as well as on our website. And remember, you can also join us for Easter revision. Bye guys.